Hello, we're going to look at the atom and how we came to this particular model of the atom. When we say a model, we mean how do we view it? How do we look at it? What do we think's going on inside an atom? Now, for GCSE chemistry and physics papers, we need to know how to label a simple model of the atom. So there are four main parts that you need to know. We need to know the protons, which are the positively charged particles in the center, the neutrons, which are the same size as the protons, but they don't have any charge in the nucleus. Altogether, the center of the atom with the protons and the neutrons are called the nucleus. And around the outside, you have the third particle, electrons, that are arranged in electron shells. So you need to be able to label a diagram like this off by heart. So what you need to do is draw it and cover over the labels and practice. Another thing you need to be able to fill in a table like this. We need to know the relative mass of each of the particles and also their charges. So the proton and the neutron both have around about the same mass. We call it 1 atomic mass unit. The electrons are really small, and they're about a 2,000th of the size of a proton and neutron. So they don't really, when we're actually working out the mass of an element, they don't really contribute very much towards that. The way I like to look at it is, if a dog had fleas and you weighed the dog, would the fleas actually contribute to its mass? Would it make it any heavier? Not really. Right, you have to also look at the relative charges of each of the particles. The proton is positive, and it has a +1 charge. The neutron is neutral. It has no charge. Neutron, no charge. And the electron has the equal size of charge as the proton, but the opposite charge, so it's -1. So for every proton in the atom, you've got 1 electron. Two other things that you need to know about the atom, you need to be able to learn these off by heart, is that the atom has a size of 1 times 10 to the -10 meters. That's really small. And we can't really normally think about things that are that small. However, the nucleus of the atom also has a radius even smaller, 1 times 10 to the -14. So that means that the atom is 10,000 times larger than the center of the atom, the nucleus. 10,000 times, 10 to the power of 4. So how did we come to think about the atom the way we have? Well, the ancient Greeks gave the atom its name. It came from the Greek word atomos, meaning without splitting. They thought it was something that you just couldn't break up, you couldn't split. In the early 1800s, John Dalton, somebody from Manchester, showed evidence that atoms were tiny, hard spheres, and they made up all substances. So now our model would be like a snooker ball. So if you can imagine a snooker ball, right, it's solid, and that's what he thought the atoms were like. only very, very much smaller. So how did we move on? Well, J.J. Thomson in 1897, he discovered that they had tiny negatively charged particles with almost no mass, and they were contained inside atoms, and he called the particles electrons. He discovered this during an experiment where beams of particles were attracted towards a positive charge. So he knew that there was a positive charge in the atom. He knew that the atoms had no overall charge, so for every negatively charged particle, there would be the same amount of positive charge. So he called this the Plum pudding model. Now, this really confused me when I was at school, because I knew what a plum pudding was from my grandma. Plum pudding is like a solid pudding, and it's got plums in it, funny enough, like currants. And the currants would be the electrons, and the rest of the dough would be the positive charge. So I grew up thinking that the plum pudding model was solid, but it wasn't. It's more like thinking of like smoke particles in a mist. This is like transparent positive cloud of charge, and things could go through it, and tiny little electrons on the outside. Okay, so this is something that's not solid, but it is a cloud of positive charge with lots of electrons in it. Okay, so that was our model so far, the plum pudding model. And Ernest Rutherford, he was working with two other scientists, Geiger and Marsden, and he did an experiment. Now, models can only be changed if they find new evidence that means the last model doesn't work. Okay, so he fired alpha particles, which are positively charged, at a sheet of gold foil atoms. What he expected was, if it was the plum pudding model, every single alpha particle would go through. However, he found that there were small numbers that didn't go through. Most of them went through, right? So he knew that there was plenty of space there, but a few of them sort of went on a swerve, and some of them bounced straight back. Okay, so how did he come to change the model? Well, let's have a look at his observations. The first observation, most of the alpha particles went straight through. Well, the conclusion he came from that for the new model was that the atom is mostly empty space. So that observation, that most of the particles went straight through, the atom is mostly empty space. The second observation, about 1 in 8,000 alpha particles, so not many, they bounce straight back. So what did he come to conclude from that? Well, he concluded that they must have hit something solid in the middle. And because it was only a few of them, most of the particles are going straight through, and there was only a tiny amount that hit them, he came to the conclusion that that centre was really, really, really tiny. Okay, and he called that the nucleus. Right, his third observation, the one where they swerve, so they change in direction slightly. And remember, we said that the alpha particles are positive, means that we had like a repelling force going on here. So he came to the conclusion that the centre of the atom that we called the nucleus is actually positively charged. So he was managing to change the plum pudding model from his observations. the atom is mostly empty space. There's a solid middle to it, and that solid middle, the nucleus, is positively charged. Okay, so the atom is mostly empty space with a positively charged nucleus at the center and negative electrons somewhere a long way away. Okay, and he called the positively charged particles protons. So we've got a new model. This is not the model that we know now, so we have to be really careful. This model was a center that's solid and positive, and somewhere outside, a long way away, are electrons. Okay, so this is the new model. We've moved from the plum pudding model to Ernest Rutherford's model of the nucleus, the nuclear model, and the electrons on the outside. Okay, after that, Niels Bohr, about 1913, so just over 100 years ago, he discovered that electrons weren't just somewhere on the outside, right? They were at different places on the outside, right? He discovered that electrons can be given more energy and go to a higher energy level. And when they come back down to a lower energy level, they give light out. All right, so what he discovered was that the electrons are in shells. So now our new model, the same like Rutherford's model, it's got a center that's positive, the nucleus, but now the electrons are in shells round the outside. Okay, we moved on about another 20 years, and James Chadwick, he discovered the neutron. Now what he did was he found that atoms of the same element with the same number of protons, which they have to be the same element, could have different masses, and we call these isotopes now. As the electrons have hardly any mass, he concluded that there must be a third particle that could add to the mass but not add to the charge. He knew that the particle must have no charge because the atoms have no overall charge, and he knew that the electrons and protons already cancelled each other out. So he said in the nucleus there must be another particle that has the same mass as a proton but no charge, and so he discovered neutrons. So this is now our new model, which is protons and neutrons in the nucleus of the atom, with what Niels Bohr said, the electrons are in shells on the outside. Now, there are further discoveries about the atom, but that's all you need to know for your GCSE. So this is like a timeline. We have the ancient Greeks and their not splitting the atom. We have Dalton and his like a snooker ball solid atom. We have J.J. Thomson's plum pudding model, which is a cloud of positive with lots of negative electrons in. Then Rutherford, he developed that from his experiment where the plum pudding model didn't fit his experiment, so therefore he's got the nuclear model of a nucleus with electrons somewhere in space outside. Niels Bohr then discovered the electron shells, and Chadwick discovered the nucleus. So let's look back at our size of the atom and the nucleus. Okay, so if you remember, we said that the atom has a radius of 1 times 10 to the minus 10, and the nucleus has a radius of 1 times 10 to the minus 14, which means that the atom is 10,000 times larger than the nucleus. So all those experiments that Rutherford did, right, he confirmed that, right? Well, let's just have a little look at what the atom would mean in terms of those sizes. So if I held up a table tennis ball in the science department, all right, that's the nucleus of the atom, which I can see. The electrons would be somewhere down the road, say at FC United. All right, that's where the little tiny electrons would be, and they would be the size of a small pea. Well, in fact, even smaller. They would be the size of a flea. All right. So can you see now that if Rutherford is firing alpha particles through, they're very unlikely to hit my table tennis ball. And you can see most of them are going to go straight through. If I was firing peas, right, at my atom, then most of them are not going to hit my table tennis ball, and most of them would go straight through. So this confirms Rutherford's alpha particle experiment, that the particles, most of them went straight through, and very, very, very few of them hit the nucleus because it is so tiny compared to the size of an atom. I hope that this helps you with your history of the atom.